all the other organizers. So this maybe is not completely clear from the title, but I hope it's clear from the abstract. I will go through the history of the search of neutral nuclei. So this is very timely because a review I have written with Jaume Carbonell has been just published in the European Physical Journal. I have the reference here. In this review, I took part of the experimental part of the history and Jaume of the theoretical part. So you will have in this reference, you have all the details of both quests. Today, I will mainly talk about the experimental quest. I will devote just one slide to the theoretical quest. I'm afraid that it will attract most of the questions, but I will talk mainly about the experimental part. And since I have gone through history, I have I accessed a lot of original papers, and I try to highlight the sentences and the conclusions directly from the papers themselves. So the first one is the neutron. So the first multi-neutron is the neutron, and 1932. This is the original Nature paper from Chadwick. And well, it was, even if he was completely sure about his discovery, the title was Possible Existence of a Neutron. So here you have some where he describes the origin of the mystery that they were trying to solve in beryllium radiation, and then how he reached his conclusion. So he irradiated several atoms, several nuclei, and he measured the recoils. And the conclusion was that the particle inducing the recoils was of mass 1 and charge 0. And then in this same paper, in the conclusions, you see one of the problems in experiments involving neutrons is that the neutron is neutral, so it has to collide with a nucleus. So he said atoms, but by atoms he meant at that time nuclei. So the neutron detection efficiency are typically a few percent. Of course, if you want to detect several neutrons, it's even worse. It's these few percent to the power of the number of neutrons at most. And here you have examples. If you want to detect 1, 2, 3, 4 neutrons, and the 1 neutron efficiency is, for example, 10%, then if you want to detect 2 neutrons is 1, 3 neutrons is 1 per mil, and 4 neutrons is even lower, 0.1 per mil. So it goes down very quickly. You have to start with a very high neutron efficiency, and even in that case, it will go down very quickly. And of course, the neutron is often scattered, so you can detect the same neutron several times. This is called crosstalk, and this lowers still even more the efficiencies. So this is one of the problems of all this physics. Then, as an introduction, well, you all know the liquid drop model. So here you have the binding energy per nucleon of most of stable nuclei. And you see that it's about 8 NeV per nucleon. And with the liquid drop, you get just 4 parameters. Here we ignore the odd even staggering. With 4 parameters, you can describe most of the masses of the nuclear chart. And so it's very easy, as a very simple exercise, to set the number of protons to 0 in this formula and see what the liquid drop predicts. And then you see that the 4 neutron system, the prediction of the liquid drop is minus 17 NeV per nucleon. So here we are at 8. So minus 17 is several meters below your screen. The trineutron is even worse. It's minus 22 due to this pairing term. So here we could stop the seminar and say no need to look for these systems. They are too far from binding. But of course, this is just the beginning. So here you have the nuclear chart. So what do we know? Here you have a neutron star that has a neutron to proton ratio of about 8. So this is this line here. So it's more neutron rich than the lightest nuclei. We know that the dineutron is unbound and that the 10 to the 57 are bound, of course, due to gravity. But in between 2 and 10 to the 57, we don't know. We have an analogy is with in atomic physics, helium-3 atoms. The dimer is unbound, and at some point you have liquid drops of helium-3 at about 30 atoms. And here you have the potentials of the helium-3, and neutron-neutron. They look very similar. Of course, the scale is not the same. But this has been used as an argument to say that maybe 3 neutrons or 4 are not bound, but at some point you will have, with this potential, some bound system. Then you have the known masses. So here you have the masses of n = 4 isotons. And in blue, you have the experimental values. This is the hydrogen 5. So you see that the binding energy per nucleon, the binding energy of hydrogen 5 is positive, but it is unbound because the triton is more strongly bound. But hydrogen 5 is lighter than 4 neutrons and 1 proton. This is the liquid drop prediction. So for tetraneutron, it's very, very low. But if you correct this simple liquid drop by a surface correction, with a surface correction in the asymmetry term, you get already something closer to the data, still unbound for the tetraneutron, but it's not so far away. And when you have a look to the energy to the first threshold in the hydrogen and helium chains, you see what is called as helium anomaly, the fact that helium-8 is more bound than helium-6. It's also called multi-neutron anomaly because you have 4 neutrons on top of an alpha particle. And also the location of the ground state of hydrogen 7 is an important piece of the puzzle, because if it is close to threshold, hydrogen 7 would mean that this anomaly would arrive also in hydrogen. So 4 neutrons on top of a triton would increase the binding. As we have seen, we have this odd-even staggering. So the first candidate for a multi-neutron would be the tetraneutron, and then hexa and octaneutrons. But of course, due to practical issues, it's easier to try to produce tetraneutrons. So that's why most of the experiments are on the tetraneutron. And just to finish this introduction, there are 2 important issues. So the first is that neutrons are unstable. So we cannot have neutron targets. It's difficult to have neutron beams. So the production of multineutrons will be difficult. And once you have produced the multineutron, the detection of the multineutron will be difficult because the efficiencies are very low. In this review, we have gone through a lot of experiments, and I try to class them in 3 categories. So the first one is neutron detection. So you are going to do a nuclear reaction trying to produce a multineutron. And then you can try to detect the multineutron or neutrons from its decay or its breakup. Another possibility, the missing mass technique, again, a nuclear reaction, and you create the multineutron in a binary exit channel, and then you detect the charged partner. So by missing mass, you can deduce the energy of the multineutron. And in the 2-step reaction, you have produced in a first step the multineutron. If it is bound, it will be able to interact with another nucleus and to produce this particle B. So if there is no other way to transform A into B, then you have proved the formation of this multineutron. Then in this category, neutron detection, so the advantages is that the detection is explicit. You can detect the breakup of a bound multineutron or the resonant decay. Of course, if you detect the neutrons, you can study the correlations in the system. The drawback is that the efficiency is very low, and that's why only 4 experiments have been done in the 60 years. In the missing mass technique, there is the main advantage is you detect only one charged particle, so the efficiency is almost 100%. Since you are deducing the mass of the neutrons, you can deduce the mass of a bound or of a resonant state. You don't care, and the mass number is well defined. But of course, you are not detecting the system, so you are insensitive to the internal structure. The cross sections to put all the protons into B are typically small. And then if you have beam or target contaminants different from A or C, then you can produce B without a multineutron. And here the main experiments, so I have recorded 24, are charge exchange experiments in this reaction or multinucleon transfer reactions. And finally, the two-step reaction. So one main advantage, you detect only one particle, but only bound states can be probed because you need the multineutron to interact with another nucleus. You don't know the energy of the system. If you see a signal, you can only infer a lower limit. If there are contaminants different from A, you can produce B without a multineutron. And of course, typically these multineutrons are supposed to be produced in a very dirty environment, like a nuclear reactor or the like. And so you can have a lot of backgrounds that may in the end produce B without the need of a multineutron. And here I have recorded 8 experiments. So curiously, the 3 reported positive signals, each of them came in one of the categories. So this is the Ganil signal, this is the Riken signal, and this is the signal from Orsay experiment that we will see in a minute. Here I just quote these 3 references that because there were only 4 experiments that were published, so that you can, if you want to check. So those here gave negative results, but belong to this category, trying to detect the neutrons. I will start with the two-step reaction first, because there are only 8 experiments. So this is the first paper I found in 1963. So they exposed in a nuclear reactor nitrogen and aluminum samples. And so this is from the introduction of the paper. It seems reasonable that tetraneutrons should be observed inside nuclear reactors. So if they exist, they could be produced in fission of uranium, for example. And then what they were looking for is a tetraneutron on nitrogen 14 could produce nitrogen 17. And then you should see the beta decay of nitrogen 17, or aluminum 27 into magnesium 28, and you should see the beta decay of magnesium 28, or gamma decay, beta and gamma decay. So they couldn't find any of those. But, and this is an interesting conclusion that applies to all that will follow, is that when you are looking for something, not finding it is not a conclusive result. So you didn't find it. It does not mean it doesn't exist, but you were not able to find it. And this was proposed by Dalitz. So this was something also I found funny in this first paper. And in 2 years later, same kind of experiment, but in this case was deuteron-induced fission. And they used other samples. They also searched for these same signals. So a multineutron, a tetraneutron that would transform these samples into something more neutron rich, but they couldn't find those signals. And then in 1977, This is an experiment carried out by Claude Detrasse, that was later director of Ganil and IM2P3. So this was done at CERN. You have a Wolframian target guarded by a high energy proton beam. And then you are supposed to produce many things here, a lot of particles. You place a zinc sample on the other side of an aluminum screen that is supposed to stop all the charged particles that are produced. And then if multineutrons go through, then they can increase the mass of the zinc isotopes. So they were looking for the production of zinc 72. Zinc 72 decays into gallium 72 that decays into, by gamma rays. And these gamma rays could be detected by a germanium detector at Orsay. So since the lifetime of these decays is several tens of hours, they place the sample in a plane that would float, that fly to Orsay. And at Orsay, they could find the gamma rays from gallium. If the tetraneutron is bound, then the octaneutron or the hexaneutron appear to be the most likely candidates. So this was very exciting at the time. Then same year, a few months later, Turkevich tried to find them with a similar setup. So proton, uranium, aluminum screen, and in this time the sample was lead-208, and he was looking for a transformation of lead-208 in lead-212, and they couldn't find this transformation. And finally, De Boer tried to find tetraneutrons also in a similar experiment, so helium-3 on tellurium target, and then trying to search for the transformation of the tellurium atoms into tellurium 132, and they couldn't find them. So this, by the end of this series of experiments, they discussed with Detrasse, and the conclusion was that Detrasse positive signal was due to an underestimation of the production of tritons here. So a lot of tritons were stopped in the screen, but some tritons went through, and these tritons could do the TP reaction, so deposit 2 neutrons into zinc 70 to zinc 72. And the reference of this paper, this reference 25, is a private communication with Detrasse. So after these few years, the question was settled. They said, okay, we thought multineutrons existed, but now we know they don't exist. And then I moved to another category. So this is the missing mass category. So here is a cleaner one because you detect only the partner of the neutrons, and you don't have all the backgrounds that you have in the activation category. Here you have, so the first class of experiments on missing mass are double charge exchange with pions. So these experiments use helium targets, pion beam, a negative pion beam, and then you detect the positive pion after the reaction. And this pi minus pi plus transforms the helium-3 and helium-4 into 3 or 4 neutrons. So what you are looking for is peaks in the energy of the pi plus that would correspond by missing mass to peaks in the energy of the 3 or 4 neutron system. Of course, since you only have 3 and 4 helium targets, you can only access 3 or 4 neutrons. So the first experiments, again, 65, very early, they found some enhancements or some, but the data were poor, and in the end they were able to explain the enhancements with just phase space. And here, this is an example from 1984, that is quite clear. In this case, Ungar, he first used as a reference the pi minus pi plus on carbon 12. So when you do pi minus pi plus on carbon 12, you change carbon 12 into beryllium 12. And so this is the pi plus spectrum of this reaction. And you see here the phase space, and close to threshold, you have a peak that corresponds to the bound states in beryllium 12. Now, when they change the target of carbon to helium, this is what they get. So the phase space and no peaks. So this is the region where you should find a bound tetraneutron, the kinematically allowed region, and you see that there are no bound, no peaks in the resonant or in the bound region. Of course, you have events, but these events are compatible with what you see beyond this region. So this region from 238 above is kinematically forbidden, and you have counts anyway. This is the background. So you see that the counts that you see in the region you are looking for are compatible with the counts of the background. Other experiments followed until the almost the year 2000. So this one, I put some mark here because it was 1999, and this was interesting to me because it was the paper that put me in contact with the field. So in 1999, I was spending some time in the LPC library, and I found a paper that seemed quite crazy, people looking for trineutrons. And then I found that they were not just fools doing one experiment, because in the bibliography, I found all these experiments already. And then this put me on the track of trying to find these systems at Ganil. And then just to finish this technique, this is another interesting case in 1979. The same reaction, so pi minus, pi plus, but instead of on an helium target, on an alpha particle that is inside lead. So you do pi minus, pi plus, quasi-free on an alpha particle, but instead of helium-4 target is an alpha particle of lead. And then this tetraneutron that you may have created can interact with another lead nucleus and lead to lead-212. So this was a quite interesting idea, but without positive result. And this is another different try in 1991, but this is quite dirty, and these sentences are from the paper itself. So they realized that the data was very poor, and that even if they quoted here a 3-neutron resonance, they were not very confident because of the data quality. Before finishing this pion charge exchange, double charge exchange, this is an interesting case. So this is pion single charge exchange. So instead of pi minus, pi plus, pi minus gamma, and then you use triton target. So pi minus triton goes into gamma and 3 neutrons. And then here you don't need to measure a pi plus, you have to measure a gamma ray. But because of the pion mass, the gamma ray is very energetic. It's about 120 MeV. So you only need to measure one gamma ray, but you need a detector able to measure 120 MeV gammas. And this is the setup. So here you have the pion beam. Here you have the triton target. You don't see the neutrons, but if you have a gamma ray of 120 MeV here, you will have a gamma conversion into into electron positron pair, and then one spectrometer that will detect the positron and the electron and will allow you to reconstruct the gamma energy. So here you have the energy is quite high. This is the result of the experiment, and this line is the result of phase space. And so the conclusion was that even if you have some structures here, they are not significant enough to conclude that there is a 3-neutron resonance. The same team, a few years later, made an improved experiment, and the data are very, very beautiful. So you see here, this is the gamma ray energy, same reaction, pi minus gamma on a triton, and you see the peak just below the threshold. So if you had a bound state in the 3 neutrons, you should see a peak here that you don't. And if you have resonances, you should see peaks here, and you don't. So the dashed line is the equivalent of phase space, is a 3 neutron plane wave, and the solid line is the same thing, but with the effect of the 2 neutron final state interaction. And you see that it reproduces very well the shift toward the threshold, and the data are very high statistics, very good resolution, and you have a perfect agreement. So you see here the conclusion saying that this experiment was done in order to be sensitive to any structure near threshold, bound or unbound, and they see no evidence for it. So this is a very beautiful result already in 1980 for the 3 neutron system. And the last category of experiments I will go through for the 20th century is the transfer reaction. So at the beginning, also 1965, the transfer was very simple. Here you have NP reaction on the triton. In this first paper, they found a bound trineutron peak, 1 MeV. But 1 year later, this team showed that this was an artifact and that there was no peak. Then in 68, they found this a slightly more complex reaction already, triton helium-3, some structure in the 3 neutron spectrum, but in all these cases, the data were very poor, and the enhancements that they call enhancements were not very clear. They were not calling them even peaks; they were just enhancements. Then in 74, this paper from Cerny with lithium-7 carbon-11 here on lithium targets in order to populate the 3 neutron with carbon-11 and the tetraneutron with carbon-10. Here you have the example of carbon-10. And this is phase space, 5-body phase space. This is the region where you should see peaks for bound tetraneutrons. And these structures here that could correspond to 4 neutron resonances come indeed from contaminants of the target. So lithium-9, boron-13, and others. So this picture summarizes quite well the status of the field in the 20th century. You do see events compatible with what you are looking for, but you cannot trust them because you have a lot of contaminants, and these events are in a region where you have backgrounds. You have still counts here and here. So you have few events that you cannot trust. Other experiments were done in 88, again, many combinations. The advantage with respect to charge exchange on helium is that here you have many possible combinations that you can try, but the results are always negative. This is a very clean experiment in 1995 from Bolen. So this is carbon-14 beam, nitrogen-13 out fragment. So what you are doing with your target is you are removing 1 proton and adding 2 neutrons. Here in the inset, you have this reaction on lithium-6. And when you do this on lithium-6, you populate helium-7. And you see here, this is the energy from lithium-6. And the missing mass tells you that here you have the ground state of helium-7. Now you do the same thing on a deuteron target, and this is what you get. So this is the 3 neutron missing mass spectrum. This is the 3 neutron threshold, no bound state, no resonant states. And again, same as the experiment with the pi minus gamma, the last one. Very high statistics, very high precision. They rule out completely the possibility of 3 neutron states. And finally, in 2005, Alexandrov confirmed these experiments from Cerny. So with this, I finished the 20th century part of the talk. And you know that there were two positive signals in Ganil and Riken. So in order to improve from all this family of experiments, we thought that we could use neutron-rich beams. And this is just a slide to show you, for those that don't know how they are produced. This is an example for the production of oxygen-28, for example, at Riken. Here you have a primary beam, calcium-48, that is accelerated, in this case to 60% of the speed of light. And then you break it. You are going to remove a number of neutrons, a number of protons, and then you create a secondary beam here with big ribs, in this case fluorine-29. And then you reach experimental room, and you just, final touch, you remove one last proton, and then you create oxygen-28 in this case. And then, of course, oxygen-28 will decay into oxygen-24 and 4 neutrons, and you need detectors here in the room to detect all those particles. But you see that in order to create this object, we need already these beams, primary and secondary, being produced. And this is just one slide for the two positive signals. So I think you may, if you have interest in the field, you may have already read about them. So this is very, very simplistic display of the results, but here you have the Ganil and the Riken result. So in the Ganil case, we have a beryllium-14 beam, and we hope to liberate a tetraneutron inside beryllium-14. So we are going to break it into beryllium-10 4 neutrons here in the reaction chamber, and then these are the neutron detectors. Neutrons are detected in a similar way as they were discovered by Chadwick. So they are neutral, so they are going through the detector, they are going to push one proton, and what you measure in the detector is the light produced by the recoil of the proton. Of course, the energy of the recoiling proton cannot be larger than the energy of the incoming neutron that you can determine by time of flight from the target to the detector. And these are, in this plot, you see this parameter. So energy of the recoiling proton compared to the energy of the incoming neutron here. And here you have the particle that was produced in this reaction. And you see 6 events that go from 1.5 to 2.2. So almost twice the recoil limit. And they all arrive for beryllium-10 channel. So this channel. So these were the 6 candidate events that were published in 2002. In 2016, these are the results from Riken, so completely different technique. This is double charge exchange on helium-4 target. So you have a helium-4 target, you have a helium-8 beam coming in. You will have double charge exchange, so helium-4 becomes tetraneutron that remains in the target area and are not detected. But the helium-8 becomes beryllium-8, and beryllium-8 decays in 2 alphas, and you measure these 2 alphas. And then the 2 alphas will tell you the missing mass of the 4 neutrons. And this is the spectrum of the missing mass of the 4 neutrons, and you see close to threshold 4 events that cannot be explained by the background estimation or by the phase space of the reaction. I would like to point out that this, so these are the references, the Ganil result. We first published with the scenario of a bound tetraneutron hitting one of the protons. Then we also proposed the possibility of a very low energy 4 neutron resonance in which that decayed in flight and several neutrons went into the same detector. And with this, we established a possibility of between -1 MeV for a bound state or +2 MeV for a resonant state. The Riken result gave 0.8 MeV resonance, but taking into account the systematic and statistic errors, were plus minus 1.3. So you see that both results, very different techniques, very different beam energies, they lead to very similar conclusions. They also have in common the few statistics, so only 6 events here or 4 events here. And then, of course, this triggered a lot of calculations. So this is the only slide I prepared for the theoretical part of the review. I just tried to summarize. So this is not an exhaustive review of the works, but I just tried to summarize the principles. So on one hand, we have exact calculations, and they are all categorical. So they started for the 3-neutron system, of course, because of technical issues. So Glöckler in 78, he modified the neutron-neutron interaction in order to have a 3-neutron bound system. And he found that the factor was huge. He needed 4 times the neutron-neutron interaction. Then in 79, they added only with S waves. They added the P waves, and in that case, they needed a smaller factor, but still close to 4. Of course, this is very problematic because if you multiply the neutron-neutron interaction times 4 to slightly bind the trineutron, then you are binding the dineutron already by more than 100 MeV. So you have a very unphysical system. You have a barely bound trineutron that contains a strongly bound dineutron, and that would decay, in fact, into a dineutron and a neutron. So in 1999, they perfected these calculations by not modifying the S wave. So they leave the S wave responsible for the dineutron, and they change all the other waves. And again, in 2002, by solving exactly the Fadeev question, and this is the kind of picture that they obtained. This is from the 2002 paper. You force the system to be bound here, and then this is the complex energy plane, and you start to release these constraints until you remove them completely, and you see where in this complex plane the resonance will end up. To guide the eye, this yellow sector is the one in which you see physical resonances, so positive energy with comparable width. And you see that when you remove completely the factors needed to bind the trineutron, you end up in a region that is completely unphysical. And the conclusions from these calculations were 3-neutron resonances close to the physical region will not exist. So they don't say should not or may not, they say will not exist. They were categorical. In the years 2000, after the GAN result, Lazauskas and Carbonell did the same thing, exact calculations for 3 and also for 4 neutrons, and they reached the same conclusions. So all the resonances ended up very, very far from the physical region. And in 2016, after the RIKEN result, they worked with Hiyama-san at RIKEN to try another thing, add a 3-neutron force in the T3½ channel, and again, they reach exactly the same conclusions. On the other hand, many body approximations from 2003, the Piper work, they said that bound systems could not exist, but this extrapolation from this work suggested that, so here you have 4 neutrons, you put them in a Booth-Saxon trap, and then you remove the trap. So here you have the intensity of the trap. When you remove the trap, you stop here, here, or here. I want for different sizes of the trap. And then he extrapolated all of them, and he said, well, when I remove for a trap depth of 0, all the extrapolations cross at about 2 MeV. So he suggested that maybe we could have a 2 MeV 4-neutron resonance, but he was very cautious about it. He said if it exists at all, it must be very broad. And then a lot of people, after this prediction and the Riken result, other many body approximations reached similar conclusions. So these are some of the main works. This is no-core shell model. This is, again, green function Monte Carlo as Piper. And these two are no-core Gamow shell model. And they all, by using factors and traps, they all predict 3 or 4 neutron resonances. Then Del Tuba and Lazauskas tried to criticize these approaches and said that these conclusions were an artifact of the technique that they use. So, and very recently, Ishikawa also demonstrated that when you try to extrapolate bound states trapped into external wells into resonances in the continuum, you can get resonances that are unreal and are just artifacts. So I will refer you to these papers if you want to know the details. And again, Del Tuba and Higgins and collaborators showed very recently that even if you don't have resonances, you may have quantum mechanical enhancements in the cross-section. So these two papers say that maybe the signals from Ganil and Riken are real, but that maybe, or most likely, they do not correspond to 4 neutron resonances, but to some enhancements in the cross-section. So I will come back to this in the summary. So just before going to the future or the short-term future, this is a summary of the experiments that we have reviewed. This is a plot of the chronology. This is the year of the publication. So I have compiled 36 works. Among the 36, only 32 were not using neutron detectors, so most of them. 14 were for the study of the tetraneutron. You have them in yellow here. There were 3 positive signals, the one from the class at CERN, Ganil, and Riken. One of them was strong, the signal from CERN, but it was refuted. And 2 that have not been contested yet were weak. So the landscape is not very clear. And then I try to guide the eye with these structures here. You see that there is a pattern in the 20th century. You have each decade, you have one experiment that triggers other experiments, and then people become tired of the thing and stop. Then someone else starts, and this happens again and again, but lower and lower. Now we will see that in the 2020s, there have been new experiments that may induce a qualitative increase. So we may have more results here and with much better quality. And this is the last part of the talk. I will try to give you an overview of what is going on in the present. So we have seen the past, the distant past in the 20th century, now the short-term past in Ganil and Riken, and now this is the short-term future. These are 3 experiments that have been already done at Riken, and that I have used to explain to you some of the issues that we have when doing these experiments. So in this case, this is the same experiment of as Kisamori, but with better conditions. So again, this is helium-8 beam on helium-4, double charge exchange. We measure the 2 alphas, and we obtain the tetraneutron by missing mass. So helium-8 on alpha, tetraneutron, and then we detect the 2 alpha particles. This here represents the detection. Another experiment is helium-8 PP alpha. So helium-8 beam, proton target. The proton will knock the alpha out. And this is measured at 180 degrees in the center of mass. So a head-on collision. So you have the alpha knocked out backward, the proton is knocked out forward, and then the 4 neutrons are left alone without interaction with the other particles. So by measuring the alpha and the proton, you can get the missing mass of the neutrons. And finally, our collaboration and group from Riken proposed this experiment. So P2P on helium-8 and try to form hydrogen-7. So here you have same beam, again, helium-8, same target and here, proton target. This proton is going to remove one proton from the alpha particle, and we are going, and then you have a triton and 4 neutrons, so hydrogen-7. And hydrogen-7 should decay into a triton and 4 neutrons, and we will measure all the particles. So this is a very simple formula. So why do we do all these experiments? The techniques are different, but of course, the number of events depend on the intensity of the beams. So here is the same beam. The cross-section, and you see that this technique uses a very small cross-section, nanobars here, this one microbars, this one millibars, and the efficiency. So since we are using very high intensity beam and very high cross-section, we can afford to detect the 4 neutrons and expect tens of thousands of events. So these analyses are ongoing. I will show you some results from our program for helium for hydrogen-7. Here you have, so the idea, so we have a primary beam at weekend, oxygen-19. We are going to break it first in big ribs. We are going to make this helium-8 secondary beam, and then we are going to remove one proton in order to create hydrogen-7. The proton from the target and the proton removed will be detected too, and then we will measure this decay of hydrogen-7 into a triton and 4 neutrons. So you see that the final state is 7 bodies. 1, 2, 3, 4, 5, 6, 7. Why hydrogen-7? So we have already measured in the collaboration oxygen-28 and its decay to oxygen-24. But in oxygen-28, you have the ground state of oxygen-26 that is very narrow and very low lying, and it seems that all decays go through this state. So it's not a 4 neutron decay, it's a 2 times 2 neutron decays. In hydrogen-7, we expect the ground state to be about 1 MeV, so it's lower than the states in hydrogen-4, 5, and 6. So we should have a direct 4 neutron decay. And the other advantage is that hydrogen-7 is much closer to stability than oxygen-28, so the statistics will be much higher. By using several arrays, we can detect the protons already, so we could measure the missing mass of hydrogen-7 with a resolution of few MeV. If we detect also the triton and the neutrons, we can go down to, so now we have the invariant mass of hydrogen-7 and of the neutrons, and we go down to 100 keV resolution. And of course, by measuring the neutrons, we can have access to the angular correlations in the decay. Yeah, so before just showing some preliminary result, this is to let you know. So these experiments are very complex and they need a lot of detectors and a lot of people. This is just 1/3, I think, of the collaboration. The other 2/3 were sleeping. And you see here the teams from LPC, SACLE, RIKEN, GSI, and China. And here you see a view of the room where you see this is the helium-8 beam. Here you have the hydrogen target. You have here the TPC and the detectors to measure the 2 protons. And then this is the dipole that will bend the triton that will be detected here. And these are the neutron walls that will detect the 4 neutrons. So a very complex setup. And before finishing this seminar, just to show you that, so the experiment went very well, and just to show you that the data are promising. This is another channel. So I told you that we create helium-8 secondary beam and that we remove 1 proton. But we can also remove 1 neutron and populate helium-7, or 2 neutrons and populate helium-6. And this will let us know if the detectors are working properly. So here you have the neutron detector. So these are 2 walls of nebula and 1 wall of Neuland. In total, you have these scintillator bars. you have 520 bars in total. This is a preliminary result from Cyril Lenant, the student that is working on the analysis at LPC. So here you have PPN reaction, you populate helium-7 and helium-7 decays into helium-6 plus 1 neutron. And this is the energy of helium-6 plus 1 neutron. And you see here clearly the ground state of helium-7 and the high statistics. Then we can remove 2 neutrons and we can populate the excited state of helium-6, helium-4 plus 2n. And you see here clearly the 2 plus state of helium-6. And again, the statistics are very high. And now you can also remove 1 neutron only, but you can populate a state, a higher line state in helium-7 that is known since 1999, that decays into helium-4 plus 3 neutrons, and that has never been detected directly because the 3 neutrons were never detected before. And this is a result that shows the energy of the alpha particle and the 3 neutrons, and you see ground state of helium-7 decaying by 1 neutron decay, and this is the excited state decaying by 3 neutron decay. So you see that we can handle the 1, 2, and 3 neutron detection. These spectra are preliminary and correspond only to 6% of runs. So you can imagine the whole statistics. And of course, Cyril is now working on the proton removal channel and the production of 4 neutrons. So we hope that in a few months, we would be able to show you results for hydrogen-7 and for the tetraneutron. And with this, I reached to my summary. So this is, I take this from the first paper I showed in this history review from 63. So the sentence that they used in the conclusion: as in most experiments of this sort, however, a negative result cannot be regarded as conclusive. Of course, what we are looking for is a positive result, but a conclusive one. So what we have seen in this chronology of experiments, that the series of these were not just individual tries of people that were that didn't know what to do. This was an extraordinary series of experiments, many different techniques, many different detectors, fascinating ideas. We have seen some very precise results on the 3 neutron system that do not find any signal of a trineutron. We have seen few weak signals on the 4 neutron case, Ganil and Ricken. So in the next few months, years, we hope that these signals will be clarified. So they will either be refuted and then there is nothing to see, or maybe they will be confirmed. And in that case, we have to, this is mostly the theory that has to tell us if these signals are confirmed, are they states in these systems, or are they enhancements in the cross sections? The perspectives of 2020 experiments are very promising. So as you have seen in the previous slide, the statistics and the resolution are very high. So it's a qualitative step with respect to the previous experiments. And even the first 6 neutron experiments are being done. So by studying the helium-10 decay into helium-4 plus 6 neutrons. On the theoretical side, we have seen that there are uncertainties. So the exact calculations are categorical, and all of them, they all agree that if there are signals, they cannot be 3 or 4 neutron states. The many body approximations claim that there can be states, there can be resonance. And even if this disagreement is a bit shocking, they all agree in one thing, is that their difference do not come from the interaction. So independently of the neutron-neutron interaction, or even in the use of 3 neutron forces, the conclusions remain the same. So these guys cannot find bound systems with other interactions of 3 neutron forces, and these guys, even changing the interaction, are able to predict resonances. most of the clues come from the technique that these approximations use. So the trap and the global scaling that create thresholds in the system, and the extrapolation to the continuum that they use. And so just to finish with some positive remarks on the theory. So of course, what the theory hopes is to have very strong experimental results that they can use as a benchmark. So if these latest experiments provide strong signals, then the theory will be able to move on with these inputs. And of course, there are two things that I find interesting. So first, the works that predict some enhancements, even if there are no resonance, they should try to characterize these signals so that they can be distinguished in experiments. And also something that is not possible in experiments today, that maybe can reach the 6-neutron system. The theory can go further much faster. So maybe the theory could tell us what is the trend in the binding of these 6, 8, and 10-neutron systems. And maybe with this combination of results, we could do a significant step forward in the field. And with this, I thank you for your attention. It was a bit longer than expected, I think. Thank you.